Kinetic and gravitational potential energy, part 1. So this marks the second half of the energy section in Physics 30. To start things off, we've looked at work done so far and changing that into useful work done per time in terms of power. We'll looking at work from an energy point of view, and we can think of the work done on an object as the change in energy gained by the object. Or, symbolically, we could think of W equals delta E, where delta E can be either kinetic energy or potential energy. We'll just look at those two in Physics 30. That energy change being either kinetic, potential, or sometimes even a combination of both. So, first of all, kinetic energy, what you're familiar with. Energy an object has due to its motion. And in terms of an equation, I'll use a big K to represent kinetic energy. Its energy is in terms of joules. And a half mv squared, where m is mass in kilograms. Velocity, loosely speaking, velocity or speed in terms of meters per second. And of course, that is going to be squared. So we can see that one type of unit is joules, also kilogram, meter squared per second squared when we work those units out. And energy, once again, just like work in terms of joules, it is a scalar quantity. It is not a vector quantity. It's not direction dependent, but we do get positive and negative values for energy. A positive kinetic energy value means that the object gains energy, whereas a negative K value means that an object loses energy. So in terms of positive, negative, that's what that means, not direction. So just a fairly straightforward example here using that idea. What is the kinetic energy of a 0.500 kilogram ball thrown 30.0 meters per second? So solution, we know what the mass is, we know what the speed / velocity is, so it's relatively straightforward, just simply substituting it into that equation, and we get 1/2 of 0.5 kgs multiplied by 30.0 meters squared, meters per second, all squared. Don't forget, order of operations, bed mass, brackets, exponents. So make sure you do that exponent first of all there. 30 squared is 900 there. So we get kilogram, meter squared per second squared, and we can simply refer to that as 225 joules. So be sure you don't forget. If you're going to make a mistake with these questions, chances are it's going to occur in that forgetting to square the speed or velocity. One more example here. How much work is required to accelerate a 150 kilogram motorbike from 10 meters per second to 20 meters per second? So here we have something else happening here. Work done, recall from earlier, if you see the word work, work is transferable to energy. Work is equal to change in energy, and in this case, we're going from 10 meters per second to 20 meters per second. So in this case, that delta E is kinetic energy we're talking about. So work is equal to change in kinetic energy. So work equals, I can simply say delta K, and of course, in terms of a change in something, we must have some final value minus some initial value. So in this case, it's kinetic energy. So I just used the little F subscript and a little I subscript, similar to all change in quantities that we use. And factoring that into, of course, 1/2 mv squared, 1/2 mv squared. The thing that makes both kinetic energies different, of course, is the velocity. V final, V initial. Okay. Thinking back to math class here, you don't necessarily have to do what I'm about to do, but you can. We have two terms here with something common to both terms, a 1/2 m and a 1/2 m. So what I did here is I factored that out. This will come into play later on and we'll see why we do that. So I just simply took the 1/2 m out. If you wanted to substitute the values in here, you could. But I chose to factor out the common term, which you can do. It's legal. So 1/2 m multiplied by V final squared minus V initial squared. So 1/2 of my mass, of course we know it's 150 kilograms. And my final velocity is 20, my initial velocity is 10. squaring both of those, and of course, you can work this on your own in your calculator. You would likely do this 400 minus 100 part first, then multiply by the mass, then take a half of that, and you get 22,500 kilogram meters squared per second squared, which of course is equivalent to joules. So that's kind of the introduction of the first part, dealing with kinetic energy.